Hello, please take a seat. This is an audience that should be highly valorized for its principled stance. You don't like hypes, and the previous panel already allowed some of the members of the audience to question technological hypes, but I think the reply of the panel members was fair enough, and it nicely allowed us to open a little bit the minds for this last panel, which is it on a hype or is it not on a hype? And I told my two speakers that there is a technology fatigue amongst data protection people. For them, every technology is processing of data and they don't want to know the specific embodiment of that processing activity. That is a very extreme and abstract position, and I see it as one of the strengths but also flaws of data protection, by the way, because I think the embodiment matters. The technologies are different. So we have a last one on quantum computing with two speakers, Deborah Nas and Maria Riesco. I'm going to introduce them one by one, but it's basically Deborah who will take the floor first. And she's a very experienced technology explainer in the Netherlands and outside the Netherlands. You actually seems to be passionate about technologies. And I discussed things with Deborah. She's not the one to give herself to a hype that she doesn't find interesting. And that evidence, that gives us evidence about the importance of this last panel, because for more than 5 years you have been working on this quantum computing technology. You are a member of the quantum.nl platform, these things.
I'll explain.
Yeah, you explain all that. I also know, and this is, I'm not from the Netherlands, I know they have something with quantum mechanics, so we will finally understand why. A competitive advantage and a vision on what's going to make the difference in the future. Anyway, if you Google quantum technologies, it is politically sensitive, and it's also becoming part of geopolitics, with China boasting that it's advanced, India then immediately reacting, we will do the same, and the American big tech promising just about everything with these things. So it is an interesting topic, and Deborah will introduce it, and then Maria will give us a law enforcement perspective. Why would Europol deal with these technologies? And both will have 20 minutes. Then I will ask themselves to comment upon each other, just and then it goes to you. So Deborah, please.
Yeah, thank you. Well, I guess the event organizer thought that they'll save the easy bit for last, right? Quantum. Luckily for you, I'm not a quantum scientist, so I'll keep it easy to understand. I am part of the Dutch quantum program. It's called Quantum Delta NL. And within that program, we have a team focusing on the ethical, legal, societal aspects. And that's where I sit. So basically, what does quantum mean for our world, for our industry? I'm also a professor at the Delft University of Technology, focused on technology-based innovation. So what if we sort of the starting point for an innovation process is a new technological capability instead of a problem to solve? How does that work? How do we go about? And how do we guide things in the right direction? Now, when talking about quantum, many people think it's very futuristic. You know, it's about the future, we don't have it yet. But actually, quantum is all around us, and it's been around us forever. And it's how nature works. And the basic of our understanding of quantum mechanics was created almost 100 years ago by these people, and they're all there. Madame Curie, Einstein, Bohr, Planck, and 17 of these people won a Nobel Prize in physics. So this is a really smart bunch of people. And they came together at a conference and started thinking about sort of how do things work at a very, very tiny scale. At a quantum scale. And thanks to their knowledge, and that the knowledge created and formalized in the laws of quantum mechanics, today we have all sorts of interesting technologies, like MRI scanners, lasers, nuclear technology, atomic clocks, computer chips, you name it, it's everywhere. And this is what we call quantum 1.0. It means that we understand the laws of quantum mechanics, how the world works at this tiny, tiny level. And we use that knowledge to create these technologies. Now we're on the verge of moving towards quantum 2.0. And this is for the very first point in time that we're actually able to manipulate these quantum particles and make them do what we want them to do. And this will give us quantum sensors, quantum communication, and quantum computers. And made possible by what we call qubits. And this is a piece of quantum information. So if we have a normal computer, you have a bit, it's 0 or 1. And in quantum mechanics, we have a qubit. And it's often said that it's 0 and 1 at the same time. It's not entirely true. It's basically a probability of being 0 and a probability of being 1. And you can compare it to spinning a coin on its side. If you take a coin, you spin it on its side on a table, you look at it from right on top, you will see heads and tails at the same time. But when you really want to know what the outcome will be, you'll slap the coin and it becomes heads or tails. It's the same with a qubit. It is sort of 0 and 1 at the same time, but if you want to know what the outcome is, you need to do a measurement. It's like slapping the coin and then it becomes 0 or 1 because you take it out of the quantum state and you bring it to a normal state. Now, there's something else which is very peculiar about quantum. That's what we call entanglement. It's like taking two coins, spinning them on their side, leaving one here, taking one to the coffee room, and when we slap this coin and it becomes heads, the other one instantly becomes tail without a communication connection sort of created by humans in between. And this is what we call entanglement. And the previous one, by the way, is called superposition. Now, these two principles enable us to create new technologies. And they are not equally far advanced. Most furthest from the market is the quantum computer. It's very much still in the research, a little bit in the development phase. There are quantum computers, they exist, but they're very weak, receptive to noise, and they can't do anything useful yet, or at least definitely not something that a normal computer cannot. I'll get to that in a bit, by the way. Then we have quantum networks, which should become the overlay for the normal internet, and we envision a quantum internet. And then we have quantum sensors, which are closest to market. So what do they do? Let's start with the quantum computers, because most people tend to talk or focus on the quantum computers when talking about quantum, because they are the most revolutionary and have the most transformative power. From the outside, they look like boring machines, but if you take the insulation off, you see this beautiful device. This is a Google one. And it's basically a system that just is a big freezer. And it cools down all the temperature until all the way on the bottom where there's a small quantum computer chip, which functions at a temperature that is colder than outer space, so minus 273 degrees Celsius, because we need superconducting to make this work. And this computer in particular, the Google one, reached what we call quantum supremacy in 2019. And that is the very first point in time where a quantum computer could do something that a supercomputer could not. It was a specific calculation, and this computer took 3 minutes and 20 seconds. And the estimate was that the biggest supercomputer in the world at the time would take about 10,000 years to do it. The problem was, though, we have no practical use for that calculation. So it was sort of created to demonstrate that it does very well and it's something that we couldn't do, but we have no practical use for the calculation itself. But it does show, it's a proof of concept, that a quantum computer is not just a faster computer, it is an entirely different type of computer. It will also not replace normal computers. It will be an addition too. And how sort of the magic behind it is explained in this video.
Quantum computers will change the world. They will help us find new materials, new medicines, and navigate cars to their destination. How do these computers work? And what can they do that normal computers cannot? Computers help us solve many problems. Some problems are solved by searching for the best solutions from large lists of options. For example, when you search for the shortest route to your destination. Quantum computers can solve such search problems more efficiently than normal computers. In this video, we will illustrate this by looking at how little animals find the exit of a maze. A normal computer finds the exit by trying options one after the other, as a ladybug that tries all possible paths until it finds the exit and the food. This works, but it's not efficient if the maze has 1,000 paths or many more. And for many real-life problems, computers have to search through lots of options. A quantum computer searches for the exit by trying all options simultaneously. This is called superposition and can be visualized by replacing the ladybug with a bunch of quantum ants. These ants march along all paths simultaneously. Does one ant from the bunch know the exit? Probably not. When you randomly pick an ant out of the superposition of marching ants, you probably get one that is exploring a dead-end path. Unfortunately, a quantum computer has the same problem. To get the solution, you need to measure the state of the quantum computer. From the measurement, you don't get the full information, but randomly just one of the solutions the computer is working on, one ant and the route it is walking on. For quantum computing, superposition alone is not enough. We also need to run a quantum program. In real life, the ant colony optimizes its efforts. Ants that hit a dead end will try other paths, and ants that return with food stick to the right path. A quantum computer works similarly. It runs a program that in time focuses the search on the good solutions only. After some time, almost all ants have found the exit. And if you now randomly pick one ant out of the superposition, it almost certainly can tell you where the exit is. If you measure the state of the quantum computer after running the program, you get the right solution with high probability. You may wonder, these quantum ants seem not really faster in finding the exit than the good old ladybug. Where is the power of the quantum computer? The answer is in the scaling. Problems with a gigantic number of possible solutions are simply too big for the ladybug. It is quantum ants that can direct your future car swiftly to your destination.
So, two things that it can help us do, or at least we think it can help us do, is solve many of today's big challenges, right? Where we run into the limits of today's computing power. So simulating any complex physical system, so developing new chemical processes, new materials, new drugs, anything that sort of works according to the laws of quantum mechanics, which is anything in nature and it has to do with materials, is better simulated on a quantum computer that also works according to the same laws than on a traditional computer. Optimization problems like the traveling salesman problem and searching unstructured data, which is probably one of the most interesting use cases for you. This is the good news. The bad news is that it's also expected to be exceptionally good in finding prime numbers, which is the basis of our public key encryption. And therefore, at some point in time, it is expected to break public key encryption. And it's not exactly sure when this will happen. Some say, so you have some startups in Silicon Valley saying 6 years. You have some scientists saying maybe never. Most experts think 10 to 15 years. So you could say, well, that's far into the future, no problem there. But if you want to migrate to a quantum safe encryption, some of the big banks estimated that it will take about 10 years to migrate the entire infrastructure. So that means starting now, right? We have quantum sensors. This is an example of a quantum sensor. This is one that measures frequencies from 0 to 100 megahertz, something that you normally would need multiple sensors for. And that's basically what quantum sensors will help us do. Either measure a much wider spectrum or a much more detailed, whatever you want to measure. We also see the first experiments with quantum navigation, which is a unjammable navigation system. It basically works by choosing a fixed point on Earth, linking that to a map, and then all the movements afterwards will be relative to that point. So there's no satellite communication or any other type of communication involved. We see quantum communication. It's difficult to visualize. It's networks, it's fiber optics. It's basically the same fiber optics we use today for the internet, but then used for something else. And it allows us to do a couple of things. For example, quantum key distribution. And that's a way to exchange keys in a very safe way. And the first pilot we have in the Netherlands is the Port of Rotterdam, because we think we will first use it in critical infrastructure. Like the Port of Rotterdam. We're now building 3 pilots or 3 networks in the Netherlands, and in the area of the Port of Rotterdam is one. It is operational. Basically what it does, it allows you to create a quantum connection, generate a fully random key, because quantum can be fully random. It's a symmetric key. You exchange the key over the quantum connection, and then use that key to encrypt your information, which you send to the other party over the normal internet. This sounds very sort of easy, but then the question is obviously how often will you use the keys? And if you reuse them, where do you store them? So new questions popping up. But it is a way to protect ourselves, so quantum offering a protection against quantum itself. There's also another way we can protect ourselves, and that's called post-quantum cryptography. And the standards have just been set, I think a month ago, by NIST. And it's called the Federal Information Processing Standards. There are 3, FIPS 203, 204, and 205. So they're now available, and I think the first one is for general encryption, and the last 2 are for digital signatures specifically. The US already announced that by 2035, everybody needs to be quantum proof, and all of the corporates have, or large organizations have an obligation to show a best effort in this initiative. So it will also hugely affect tender processes and everything. Whether or not these standards remain quantum proof is yet to be seen, obviously. Because by now, or today, quantum computers, it's still theoretical, at least the large-scale quantum computer that can break encryption. So these are lattice-based or hash-based, different than factorization. Something else that's interesting about quantum networks is that it can create unforgeable verification of digital data. So there will be quantum digital signatures, which you could see as a next version, the evolution of the normal digital signatures. There's something that we call quantum electronic voting, where people can, for elections, for example, you can place your vote in a completely anonymous way while being identified. And into the system is baked sort of that you can't vote twice. We have quantum position verification. So being 100% sure that a message is sent from a specific location without the need to identify the sender. Quantum fingerprinting, making sure the data is authentic, and quantum money, unforgeable version of digital currency. Now, this is still theoretical. So there are academic papers about it. If you really want to know the details, you need to speak to that specific researcher. This is not something you can already try out, but they're the first signs of what could it do. And then last but not least, we have the opportunity through quantum networks to connect quantum devices. So for example, quantum sensors, one of the most known use cases is putting quantum sensors in telescopes, and they're across the world, and connecting them through a quantum network allows you to entangle them. And when they're entangled, they will start functioning as one, allowing us to look back in space much further, sort of look back in time much further. Or connect multiple small quantum computers together through quantum networks, enable them to function as one large quantum computer, bringing that point in time where we can break public key encryption maybe much closer. Another interesting thing for you might be to know that if somebody connects to a quantum computer through a quantum connection, nobody can see what that person is doing. Because in quantum, we have what we call a no cloning principle. When you want to copy a qubit, it's basically the same effect as a measurement. You take it out of its quantum state, meaning that the person having the connection immediately notices. And you change the outcome. So there's no way of tapping into a signal. Also, there's no way of looking into that computer. What are people doing on that computer? If somebody wants to design a chemical bomb, you don't know. Because again, if you want to look at what people are doing, you're taking measurements, you're changing the outcome, you're interfering with the calculation. So that raises all sorts of new questions. And it's likely that we'll see quantum devices we've never ever heard of and connect them through quantum networks. And it's really difficult to imagine or envision what that could mean. Now, I'm part of the Center for Quantum and Society, where we focus on the ethical, legal, societal aspects. And so, for example, we look at questions like when these types of devices, this is IBM's design quantum system 2, which is modularly designed for multiple quantum modules to be connected together, but also integrated in super computing centers. So when these things are integrated in computing centers in the cloud, do we want everybody to access that? We can't see what they're doing. So you can put it in the rules or the regulations, but if you can't enforce the regulation, what's the value of the regulation, right? So our researchers, academic researchers, especially in Amsterdam, are looking into who should be able to access a computer and how do we enforce it. We look into questions like export control. Which part of quantum technologies should be subject to export control because they can be used for commercial purposes and military purposes. And we look into the quantum divide. It's by so far a game of the rich countries, right? It's basically the US against Europe against China. Who will be first? But a large part of the world is just, not participating because of a lack of funding, especially. We have a whole team of academic researchers at the UvA, at the Information Law Center. These are some of them looking into standardization processes, the governance of quantum data, who should be able to access quantum computers, and how do we govern things. If you're interested, drop me a note, and I'm happy to put you in touch. And, if you have any other questions about quantum, or you want to raise awareness in your own organization, also feel free to reach out. Thank you very much.
Thank you, Deborah. As we're all soaking this in, while Maria goes to the platform, I can take a question perhaps first, allowing Maria to, or we can go on, and then I get probably better questions. Is it the second option? Yes. Then I'm introducing Maria Riesco. She's from Spain. She is an engineer. She worked for the Spanish police in areas such as cybersecurity. She was on the ground leading investigations, and that, of course, caught the attention of Europol with a good human resources AI. And in the past 5 months, she has been working in this venue. And I think in the Center for Innovation that was mentioned in the previous panel, exploring the relevance of new technologies from a law enforcement perspective. So that was you have the floor.
Thank you, Paul. So here in law enforcement, we have a lot of discussions about why quantum is important. Is it really something that we need to have a deep look or not? Because we have urgent cases that we need to attend, and of course, limited resources. And I am of the belief that yes, we need to make the effort of being aware of these technologies. As Deborah perfectly explained, we have a very big threat coming from quantum technology. That is that the cryptography system, like it works nowadays, is going to crack entirely. So the quantum has already solved, has already proved the ability to crack the current crypto mechanisms that we have implemented nowadays. And we rely on this cryptography to secure the information that is stored in a database, our secure communications, but every service that relies on cryptography, for example, digital signatures, or even the entire cryptocurrency system. And whether this quantum technology is going to be really in place in reality 20 years from now, we don't know, 10 years from now, depending on who you ask, is it something that we need to protect now? Because not only criminals, but also companies, people in general that are interested, they can do what it's called harvest now, decrypt later, or storage now, decrypt later. So companies, criminals, everyone is gathering information that is encrypted and is secure and it's protected nowadays, but they will be able to decrypt it in the future. For that reason, we need to protect it, to protect our information now. And I want to tell you what are the public authorities doing and what is the role of law enforcement in all this kind of protection or all this post-quantum cryptography transition. How is it called? Whoop. Okay, so as law enforcement, we work in national security. We are in charge of protecting our citizens. And for that, we need to protect first ourselves, our public services, and also the services that we provide to the citizens, and then the citizens, the industry itself. So what are we doing? The Commission, the European Commission, launched a call or a paper in April this year, 2024, with some recommendations to encourage or to foster a roadmap to post-quantum cryptography. And it needs to be done in a coordinated way. So there are a lot of public agencies, standardization bodies, also the industrial or the stakeholders from the industry needs to take place on this, cybersecurity researchers, cybersecurity professionals as well. So we all need to work together to see how are we going to transition to post-quantum. What does that mean? That we need to protect our information now. We need to protect our systems now, no matter that the technology, it will come in the future or not, because probably if it's not quantum, will be a different thing. But the cryptography, like we know it nowadays, it needs to evolve. And we need to implement with what is called quantum-resistant algorithms. For that, the Commission launched this paper. So the NIST group, and also together with ENISA, they are working together and develop some standards, which protocols are we going to use. And once that we know how we're going to do it, we need to develop a roadmap within the next 2 years to do this effort together and combined with the member states so that they all protect their public infrastructures and also to encourage the private sector to do the same. For example, here at Europol, we are working, or we are part, or we are supporting, better said, we are supporting what is called the QSFF, Quantum Safe Financial Forum, because the financial private parties, so the financial companies are already aware of this, and they claim our attention and our support to be able to aware their own councils so that they can take the proper measures so the financial system doesn't crack when this comes to place. So, sorry, from Europol, we are supporting this initiative for the financial sector, but we will be also, together with the Commission, coordinating the effort of the member states to update their algorithms to quantum-resistant algorithms and protocols so that we can all be saved as soon as possible, because we are not nowadays. And besides that, on the side of the United States, the NIST this year has also launched some call looking for the perfect standard to solve this case, or which algorithms are we going to use in the future. Still, no recommendations have been done, but we are on the same field. So let's see how this evolves. As I say, the aim is to develop a roadmap within the next 2 years. So still working on that standardization and how can it be implemented in all the member states and at the same time, not only in the public infrastructure, but also in the private ones. And ourselves as law enforcement agencies, or even Europol, we need to protect ourselves as well, like another agency or like any other institution. So we need to review our transition roadmap, or to create one if we don't have one, and see how can we implement these post-quantum algorithms or quantum-resistant algorithms so that we are protected in the future, and our communications are protected in the future. And from the criminal perspective, we have always these two sides of the coin, right, of these technologies. The bad use that the criminals do of the technology, and also how we as investigators can benefit from the evolution of the technology. So coming back to the main threat that the quantum technology presents, that is the de-encryption of information, this harvesting now and then de-encrypt later. The criminals will benefit from it because they are already having or searching a lot of information, leaked database, everything that they can take, that in the future will be revealed. And what is it gonna mean? Or yeah, what is it gonna mean? Is it only that we will be able to have a look at the, I don't know, conversations between the president of the United States and the president of China in the future? Not at that moment, but we will be able to know the information in the past, right? So a lot of sensitive information will be revealed, but this sensitive information will also contain personal information and credentials that the criminals will use to commit cybercrimes, to do phishing campaigns, to launch any campaign that needs to or is related to social engineering. So a lot of personal information will be available for criminals in the future if we don't protect ourselves now. From the other side, from the investigation side, well, one more thing. The criminals, we will say that maybe they don't have access to quantum computers so quickly, right? Because you need to be a big agency, or you need to have a lot of money because it's an expensive technology and a very advanced technology. So maybe unless a national state or a big institution provides them with these capabilities, maybe they are not able to use the quantum computing. Yes, there will be cloud-based solutions, so it will erase what we call a quantum as a service. So quantum possibilities will be available for them as well. And on the other side, on the side of the investigation, we can also de-encrypt in the future what is encrypted now, which is very useful to be able to investigate cold cases. We will have new possibilities of cracking passwords, also them. And we will have new techniques for forensic solutions that will allow us to extract more information from devices of criminals. They will also be able to use this technology, so they will also be able to crack passwords easily, so we will rely on two-factor authentication and other cybersecurity measures. And also they will be able to access our devices more easily, but we will need to take advanced cybersecurity measures. What else is gonna make possible the use of quantum? The use of quantum is gonna allow us and them to analyze larger data sets. So they can also make a better use of machine learning and artificial intelligence technologies. They can do artificial intelligence malware-based crime. They can enter into the systems easily using artificial intelligence. And we will be also able to do more efficient investigations thanks to the complex analysis of large data sets, thanks to machine learning and artificial intelligence. What they will do easily as well, thanks to quantum, with these AI improved capabilities, is everything that is related to content. For example, the creation of deep fakes that can be used not only for cybercrime, but for every kind of impersonation, whether it's terrorism, drugs, or grooming, or any kind of crime. So see the both sides, the criminal side of the use of better and enhanced AI, artificial intelligence, and the use of law enforcement in the same sense. We will both benefit of having highly secure communications, because in the future, nowadays, we're saying that we are not safe with the use of this cryptography that we have nowadays. But in the future, we will have post-quantum algorithms, which will make them even better, because the key distribution of the key that are going to be used in cryptography will not travel thanks to this property of entanglement. And so we will both benefit from having more secure communications. It will be a challenge for us to de-encrypt their communications, but at the same time, we will be safer than before. And the last thing that, because we spoke about quantum computing, which we will have quantum computers, we will have also quantum communications, but we will also have quantum sensors. And that is going to be very useful for law enforcement in terms of precision or an acquisition of traces in a crime scene, not only for digital evidences, but also for drugs, biological evidences, also for chemical evidences. So it will be very, very precise, very accurate, and we will provide better information to our judges. And to finish with this part, where is it? Yeah, here, sorry. Here, yeah. I would like to share with you this report, The Second Quantum Revolution, by the Europol Innovation Lab. It was published last year, so we've been talking about the European Commission and the NIST, how they are working on developing a roadmap this year, new algorithms. And this was already last year, and we can have a perspective of law enforcement on all these quantum technologies, how are going to affect us as agencies, but also how criminals may benefit from it, how law enforcement may benefit from it. So I can be nothing but proud of this report that was super early in 2023, last year, for this technology. So you can have a look. It's very, very interesting. We are also working in an initiative called Police. It's a consortium with 21 parties, and it's in charge, as you know, the citizens allows law enforcement to how is it called? To interfere communications in the case of serious and organized crime. So since encryption is a thing, and more when post-quantum encryption will take place, we will have difficulties to access this kind of information when even, of course, with judicial authorization. But it needs to be technologically possible to keep doing what we were allowed to do. And it's becoming more difficult thanks to technology, so we are working on that to be able to access information when it comes to serious and organized crime investigations. Yeah, and this comes from the report of my colleagues, the Europol Innovation Lab, and it's the recommendations about what law enforcement should do, and how are we going to work, or what should we do to adapt to quantum cryptography. It's mainly generic, but of course we will keep an eye on the trends, how it evolves, but we need to foster research and development projects and start experiment. As I said, this is not something that is coming in the future. The threat is now in place, so we need to act now. And for that, we need to raise awareness. And of course, we need to review as an agency our transition plan to post-quantum cryptography to be aligned with the rest of Europe and with the rest of the world, of course, because also systems need to be interoperable. And I would like to finish with this quote that I like. It's not the strongest or most intelligent of the species that survives, but the one that's most adaptable to change. And this is something from the 19th century, Charles Darwin on the origin of the species. So don't be the strongest or the smartest. No, you need to adapt to change. So I want to encourage you and invite you to embrace change, whether your organizations, if possible. I know that you have a lot of technologies that need to be aware, and it can be a bit tiring, but this is something that is going on. So embrace change and be prepared for what is coming, and just I don't know, join us in protecting the citizens also in the digital world. Thank you so much.
Check. Thank you, especially with the last call for immediate focus on change. I was like, my breath was taken away. So I need some time to fall back on my feet. But Deborah, you have listened to Maria, and Maria, you have done the same. That was very loyal to each. But Deborah, you have first reactions to what you've heard from the law enforcement perspective?
Yeah, I think I want to add to your call to action. And what I notice in practice is, because quantum is a rather difficult topic, or at least it's not that easy to understand, please be aware that you don't have to understand how it works. You know, go to the level of the spinning coins and then figure out, okay, it's quantum computers, they can break encryption. What does that mean? Sort of don't get drawn into the technicalities of things, because even the quantum scientists can't explain a lot, right? There's some things we just don't know why it works, but we know that it works that way. So yeah, I would say get people together, get a multidisciplinary team together, not just technical people, and try to figure out, okay, if this happens, what does it mean for our activities or for our line of business?
Yeah, if I can add something, also, like, it doesn't matter if it's the quantum, and don't get involved with this big word. I have a colleague that is around there in the back. He says it doesn't matter if it's quantum or if it's the aliens, but our security systems will get old at some point, and we need to work on that now. So it doesn't matter the specific techniques.
All right, I'm gonna, yes, let's fire questions, because we rarely have these two specialists together. So there's a question over there. I'm gonna take them one by one.
Yeah, by the way, the questions will receive a t-shirt.
T-shirt, yeah. You were supposed to throw out the t-shirts.
Okay, later with t-shirts. I have one question. I don't know even if it is my question proper, because I don't understand the quantum and was so fast for me, so I couldn't breathe even. And then you make a new remark on the what Maria presented, so I had another question to this. So first, how you see possibilities to complement law enforcement needs and academia efforts or findings in the discussion who can have access to quantum so-called tools? Do you see any boundaries? This is a question for you, Madame. And I don't know, when you challenged us with this, you don't need to understand how it works. Don't get drawn into details. This is what you just said. I'm a law enforcement agent and I have a problem with this statement. If I'm in front of the judge in the courtroom, I have to explain and I really have to provide the evidence that what I use is effective, legal, lawful, etc., etc. I don't need to count all the principles, right? So we have a problem here with the quantum problem for judicial authorities. And even though when the police are trying to use the tool, any kind of tool, we always ask ourselves, okay, who will have the access to data if I use the tool? It's like Google search. Oh, Google will get the data right away since I will Google it, right? And same goes with the software tools and any kind of techniques. So I think we have a lot of challenges here.
I think that's actually 3 questions. Let me start with the middle one. I understand that when you're in front of a judge, you need to be sure that what you're saying is correct. But I meant with don't get drawn into the details, I meant the quantum details. Make sure there's some quantum experts around the table, but don't make the discussion about the technology. And because before you know it, you'll be having a philosophical discussion about quantum effects. So that's what I meant with don't get drawn into the details. There's one other interesting aspect when you are in front of a judge, and that is normal computers are deterministic. Quantum is probabilistic. So if you remember the movie with the quantum ants, there's a saying that says, or there's a sentence that says, when you now do a measurement, you get the right path to the exit with a very high probability. But it's never 100%. It's still a probability. What does that mean in legal terms? I don't have an answer. But we are getting a lot of legal questions. And that's why we also have a team of academic researchers at the UvA looking into those questions, because there's a lot of, we have more questions than answers at the moment. Yeah.
From my experience that I am also a police officer and I've been dealing with investigations half of my life, it's not, I mean, it's very important to be accurate and to explain everything to the judge, but in the end, the judge will take the final decision. So imagine you have a case that it's only based on statements and you cannot really prove it if they are saying the truth or not. In the end, the judge will decide. So here, you can be as accurate as possible, and the technology will have an explanation and you will be able to provide it, but also not every system is going to be analyzed by the judge, but you will have the counterpart to analyze it for you if he doesn't agree. But the judge will take a decision after, but yeah, there are a lot of challenges that come from it. It's not that easy, yeah. I
see you nodding no, but that is like a superposition, and it can become a yes if it falls. But I saw another, did you have a question here? Yes, you, please. And then I take your question, and then I look to the right side, so your question.
My questions are real questions. I mean, I would like from Deborah to hear a bit on your part where you said that you never know what somebody does in a quantum connection, so into the computer, which is a bit striking because it changes our fundamental perception, because normally we can trace what somebody does in a computer unless we think that by end-to-end encryption we cannot. So, but this is because this is fundamental. I would like you to explain it a bit better. And whether, because now you said that quantum works on the basis of probabilistic and not determinismus. So is that different than other AI systems where we have again the probabilistic approach? And
yeah.
where we are already developing some regulatory solutions. Therefore, I'm asking.
For the first question, so the point with quantum is that there's a quantum state and there's a non-quantum state. And when it's in a quantum state, it can be multiple things at the same time. You can do entanglement, it has superposition. When you do a measurement, it falls back to two options, 0 or 1. It loses the quantum information, basically. If you want to copy data, you're actually doing the same thing as doing a measurement. You want to know what the thing is and you want to copy it. So you're taking that qubit sort of out of its quantum state. And at that moment, when you try to copy a qubit, you're actually changing it to 0 or 1 and copying that. So that makes it impossible to copy. That's also the principle for quantum key distribution. When you create a quantum link and you generate a random symmetrical key, people can tap into your quantum connection, but you will immediately know that somebody tapped into it. And you abort and you start again, basically. It's the same with the quantum computer, a quantum connection to the quantum computer. And I've had discussion, we don't know actually sort of how that will play out. At some point, you want to know the outcome of a calculation. So you have to take it out of the quantum state anyway. So that could be a point where you could copy the information. You maybe could make regulation that says using quantum connections to a quantum computer is not allowed, or it's only allowed by certain people or professions or organizations. Or maybe you can create regulations where you force big tech companies, for example, who offer those services in the cloud to not offer that service. So you can't make a quantum connection, or you can make a quantum connection so you're sure it's safe as an end user, but that provider takes it out of quantum and being able to see what's being done and then puts it into a quantum computer, but then that makes blind quantum computing impossible. So we don't really know where to solve it, or if you want to prevent that from happening, where to prevent it and how to regulate it. I don't have an answer how to do it, but is my explanation, is it a bit more clear why it's difficult to copy quantum information? It's copying is measurement, and measurement is taking it out of quantum and turning it into a 0 or 1. Yeah.
Perhaps other questions will bring us enlightenment, more building up. Huh? There were questions here, but yeah, you raise your hand. Bart, you come afterwards.
Thanks very much. I just want to continue the question on the audit aspects of this. So just so I understand, there's a difference between the processing by the quantum computer and the measurements being carried out by the user. So it would still be possible, surely, to audit and have a log of an individual user and the choices they were making to measure from the quantum computer, even if each measurement is different at the time it's taken. Would that be a way to kind of, because otherwise there's a real challenge here in terms of us having a framework for oversight of use of this technology. If we can't track and log user activity, it's very difficult for us to get the assurance.
I think you can log user activity in terms of who makes a connection when, where, but you can't copy the information that's being sent. Yeah. As we think it will now work, unless we put measures, hardware or software measures in place to make that differently. Can you add to that?
Yeah, what I'm thinking is that we are talking about the technology, but a lot will be developed over the technology. So we will have applications, we will have software, and they will all keep records. So in the end, we will be able to keep track about specifics, but it will be necessary to see case by case what technology is used. But we are talking about the technology underground, let's say, and we will not using it directly like a scientist.
I'm also not sure if there's a big difference though with today's situation, because maybe you can copy the information, but if it's encrypted, you can't see what's inside anyway. So maybe the difference isn't that big.
Yeah, I mean, from what I know is that new vulnerabilities will apply in this quantum system. So there will be new exploits and new way of accessing information. And also the key is on how are we going to get the keys that allow you to de-encrypt that information. And that is way more secure thanks to the property of entanglement, because they don't travel like now around a cable or around the specific channel. They will be just shared directly without traveling in between. But of course, there will be ways of hacking a quantum system.
Okay, I'm looking at Jan. Jan, I'm 2 minutes over time. Can I take 2 more questions? Yeah, so there was Bart first, and then on the right-hand side of Bart. And I'm sorry for the persons at the left, but we're already thinking of repeating this panel next year with these panelists. Okay.
Yeah, you should. I'm in favor of that. Thank you so much, Deborah and Maria, for the presentation. It's the first time I really got the whole concept of quantum computing and what it means. And I myself am a privacy and data protection lawyer. And also thinking about ready to change, basically. Should we also change as data protection lawyers? And should we maybe change the GDPR and the law enforcement directive to really address these issues raised by quantum computing in terms of encryption, in terms of what counts as personal data or not? Maybe you have an opinion on it. Maybe Professor De Hurt is even capable of saying something about that. How should we really be ready for the future for quantum computing?
From the regulatory perspective, if I can say something, the GDPR, it's already okay as it is. It focuses on personal information. And I think the rest of regulation will have to complement the GDPR. And it's very similar, in this case, it's very similar to the artificial intelligence regulation in terms of the amount of data that we are going to be dealing with and how can this data be exposed. Or in terms of cybersecurity, we have the NIST directive. So its area is covered by its specific regulation. So of course, we will need to create new regulation regarding quantum computing or the use, and it will be totally aligned with the GDPR. But I don't think that changing the GDPR is the main focus or what we need to focus now. But yeah, it's important.
Was one more question there over?
Okay, good.
We don't hear you. There are a lot of t-shirts here. I'm not going to throw them, but please afterwards come and get them. Yes, they have market value. I don't like orange, but
okay.
Yellow.
Since quantum sensing is around the corner, I've heard that in several places. It also has that challenge of not being detectable. So we will have more able surveillance that cannot be detected. And that's a real challenge coming up as well that you haven't mentioned. And it also relates to that question on, what to do about it. And I mean, since we're doing awareness raising, at Europol. I'm sure you're working on this, but it's important to think about that as well. And there are people who are thinking about this already, or have been thinking about it. Jay Hoofnagel, he was at CPDP last May. He went into this in depth, so that's maybe something to think about. But what I also wonder is international cooperation on quantum. If you could add a little on that. You've mentioned NIST, post-quantum cybersecurity, but are there other standards that you are looking at or that are useful as we move into regulating quantum technologies?
Yeah, thank you for your comment. In the first case, in the case of surveillance, it is true that the sensors are going to be more difficult to detect. We can forbid that, but it will still happen. So it's also a challenge for us, and we will need to work in the technical issues on the one side and not only on the regulation to be able to find countermeasures in that sense. And with your regarding to your second question, the US is taking the lead. The European Union is doing it on their side. We all cooperate together also inside the NATO framework. We work on that, but the standardization bodies are the ones that we usually rely on, which are the ITU, the ITUs and CENELEC, so the ones in charge of technology generically. But this is like a race, as someone mentioned before. So China is having their own race, Russia is having their own race to see who gets the first quantum computing to be able to de-encrypt all the information that they want. And this is very, very, very new. It's brand new. So there are not even standards that have been internationally agreed yet. So the European Commission is working on that. It's starting to work on that together with the NIST group and ENISA. And the NIST is working on that with a public call that was mainly covered by IBM and Google, but still nothing, not international standards in place. So this is in a very starting point.
Yeah, we expect the standards for quantum internet to be set in Europe because we're leading that technological research. Actually, Delft is for a large part doing that and also coordinating the European internet project. But for computing, it's different. And I think we didn't talk about that, but you have the quantum computers that need to be cooled down, which are the superconducting quantum computers. You also have photonic quantum computers who operate at room temperature. And we see that the commercial and the geopolitical elements are now converging. So, for example, the best funded quantum startup makes a photonic quantum computer. They were based in Silicon Valley. They raised 650 million to develop that quantum computer. They ran out of money. And about half a year ago, Australia figured out we're behind in the quantum race. We don't want to be behind. So they offered a startup $1 billion. For them to move their headquarters to Australia. And now they're ahead. All of a sudden, a lot of public money is pouring into quantum startups because everybody sees it might offer a geopolitical advantage at some point. And those types of developments also will have a huge impact on standardization and which standards will take off.
In case of the European Union, there is some measures that are taking place, and it sums up to 24 million euros. So it's probably not comparable to the 650 million euros in place, plus $1 billion over there. But the good thing is that they are allies for now.
All right, Maria, Deborah, thank you, and let's give them a round of applause.
Thank you.